Hello everyone, welcome back to my YouTube channel. Today we are diving into some basic principles and techniques of organic chemistry from CBSE Class 11. In the last unit, you learned about carbon's unique ability called catenation. This allows carbon to form long chains and rings by bonding with itself. Carbon also bonds with other elements like hydrogen, oxygen, nitrogen, sulfur and halogens, creating a vast variety of compounds. These are studied in a specialized branch of chemistry called as organic chemistry. Organic compounds are the backbone of life on Earth. Think about DNA, the molecule carrying genetic information, or proteins that make up our blood, muscles, and skin. But it doesn't stop there. Organic compounds are all around us, in clothing, fuel, plastic, dyes, and even medicine. About 200 years ago, chemists classified compounds as either organic coming from plants and animals or inorganic sourced from minerals. A Swedish chemist, Berzelius, believed a vital force was required to create organic compounds. But in 1828, F. Vogler shattered this idea when he synthesized urea, an organic compound in the lab from ammonium cyanide, an inorganic substance. This marked a turning point for chemistry. These discoveries proved that organic compounds could be made in lab without any vital force. Finally, the introduction of electronic theory of covalent bonding revolutionized organic chemistry, explaining how atoms bond to form molecules we study today. Understanding the molecular structure of organic compounds helps us predict their properties. Now, let's dive deeper into carbon's tetravalence and how hybridization plays a role in shaping molecules like methane, ethene, and ethane. Carbon forms covalent bond by hybridizing its s and p orbital. This hybridization affects bond length, strength, and even electronegativity. Hybrid orbitals with more s character like sp are close to the nucleus, forming shorter, stronger bonds. Meanwhile, sp3 orbitals with 25% X character are further from the nucleus, resulting in longer, weaker bonds. sp2 falls between. This greater S character also increases electronegativity. A carbon atom with a sp hybrid orbitals is more electronegative than one with sp2 or sp3 orbitals. This property influences the molecule's physical and chemical behavior. Now, let's talk about pi bonds. In a pi bond, two adjacent p orbitals overlap sideways, creating an electron cloud above and below the plane of the molecule. For example, in ethene, all the atoms lie in the same plane and the p orbitals are parallel to each other, perpendicular to the plane of molecule. In organic chemistry, representing the structure of a compound is crucial to understanding its properties and reaction. Let's explore the various types of structural representation used in organic chemistry, starting with the basics. First among the list is complete structural formula, which is also called as Lewis or dot structure. It represents every bond and atom completely. The examples of complete structural formulas of ethane, ethene, and ethane are shown in the image. Each dash represents a bond, 1 dash for a single bond and 2 for a double bond and 3 for a triple bond. Lone pair of heteroatoms like oxygen and nitrogen may also be shown in some cases. To simplify things, we use condensed structural formula. This helps avoid unnecessary details while maintaining clarity. For even further simplification, we use bond line structure. In this, carbon and hydrogen atoms are implied and only carbon-carbon bonds are drawn in a zigzag pattern. This junction and terminals represent carbon atoms. Functional groups like oxygen or halogens are clearly shown, making it easy to interpret this structure. For cyclic compounds like cyclopropane or cyclohexane, bond line formulas use polygons to represent the ring structure. Organic molecules exist in 3 dimensions and we can represent their 3D shapes using wedge and dash formulas. In this, a solid wedge represents a bond projecting out towards the observer. A dashed wedge represents a bond pointing away from the observer. A regular line shows bonds lying in a plane of the paper. To visualize these structures even better, molecules models are used. There are 3 common types. The framework model focuses on the pattern of the bonds while ignoring atom sizes. The ball and stick model shows both atoms and bonds space filling model depicts the actual size of atoms based on their van der Waals radii, emphasizing the molecular volume. Organic compounds exist in vast numbers, with even more being discovered regularly. To make sense of this diversity, we classify them based on their structure and functional groups. Let's delve into the classification system. First, we have acyclic compounds. These consist of straight or branched chains of carbon atoms. For example, compounds like ethane, isobutane, acetaldehyde, and acetic acid fall into this category. Next, we have cyclic compounds. Cyclic compounds are further divided into acyclic and aromatic compounds. Alicyclic compounds are aliphatic compounds. These contain carbon atoms arranged in a ring structure, such as cyclopropane, cyclohexane, and cyclohexene. In some cases, the ring can also include heteroatoms like oxygen, nitrogen, or sulfur. Such compounds are called heterocyclic compounds. For example, tetrahydrofuran. Aromatic compounds are special cyclic compounds with unique stability due to delocalized electron. Benzene, aniline, and naphthalene are common examples of aromatic compounds. Aromatic compounds can also include heteroatoms in their rings, known as heterocyclic aromatic compounds. Examples include furan, thiophene, and pyridine. Some aromatic compounds like trophone are called non-benzenoid compounds because they don't contain a benzene ring. Another way to classify organic compound is based on functional group. A functional group is a specific atoms or group of atoms attached to a carbon chain that defines the chemical property of the compound. The carboxyl group, the hydroxyl group are examples of functional group. Organic compounds are also organized into homologous series, where each member share the same functional group and differ by CH2 unit. Finally, we have polyfunctional compounds which contain two or more identical or different functional groups. For example, tartaric acid has two carboxylic acid groups, while amino acid contain both amino and carboxylic acid group. Organic compounds deal with an astounding variety of compounds, millions to be exact. To organize and identify them effectively, chemists rely on a systematic naming method called the IUPAC system, short for International Union of Pure and Applied Chemistry. This method allows us to deduce the structure of a compound just from its name. But before IUPAC system, names were assigned based on origin or properties. For example, citric acid comes from citrus fruit. These traditional names, known as trivial or common names, are still widely used today because systematic names can often be lengthy. For instance, the newly discovered carbon cluster C60 is popularly called Buckminster fullerene because its structure resembles the geodesic domes designed by architect Buckminster Fuller. Such names, while informal, are indispensable in many contexts. IUPAC nomenclature is based on identifying the parent hydrocarbon and functional groups attached to it. Hydrocarbons, which consist only of carbon and hydrogen atoms, are categorized as saturated, containing only single bonds, or unsaturated, which include double or triple bonds. For saturated hydrocarbons, the systematic names belong to a series called alkanes. Straight chain alkanes are named with a suffix "ane". Their prefix indicates the number of carbon atoms. For example, methane has one carbon atom, ethane has two, and so on. These names form a homologous series where each compounds differ from the next by a single CH2 group. Things get a bit more interesting with branched chain hydrocarbons. These compounds feature small carbon chains or branches attached to the main chain. These branches are called alkyl groups and are named by replacing the "ane" suffix with "il". For example, methane becomes methyl. Abbreviations like Me for methyl, ET for ethyl, and PR for propyl are often used for simplicity. To name a branched chain alkane, first we have to identify the long carbon chain and name it as the parent chain. Number the chain so that the substituents get the lowest possible numbers. Then use prefixes like di, tri, or tetra if the same substituents appears multiple times. Then list substituents in alphabetical order, ignoring prefixes like di or tri, but considering terms like iso and neon. For cyclic compounds, we simply add the prefix cyclo to the alkane name. For example, a 6-carbon ring is called cyclohexane. If there are branches or substituents, follow the same rules for numbering and naming. Functional groups bring unique reactivity to organic molecule. For example, the OH For example, the OH group found in alcohol like CH3OH reacts with sodium to release hydrogen gas. When multiple functional groups are present, one is chosen as the principal group based on a priority order and the other are treated as substituents. Isomerism is a fascinating phenomenon where two or more compounds share the same molecular formula but exhibit different properties. These compounds are called isomers. Let's explore the types of isomerism. First, we have structural isomers. Here, compounds have the same molecular formula but differ in the way atoms are linked. In chain isomerism, isomers differ in the arrangement of the carbon chain. For example, butane and isobutane share the same molecular formula C4H10, but one has straight chain while the other is branched. Position isomerism occurs when compounds differ in position of a functional group or substituents on the carbon chain. For example, in C3H8O, the hydroxyl group can be at different position, forming propan on all or propan to all. Functional group isomerism arises when isomers have different functional group. For instance, the molecular formula C3H6O can represent an aldehyde like propanol or a ketone like propanone. In metamerism, compounds differ due to variation in alkyl chain on either side of a functional group. For example, C4H10O can form methoxypropane or ectoxyetane. Moving to stereoisomerism, these isomers share the same covalent bond but differ in the spatial arrangement of the atom. Stereoisomerism can be further classified into geometrical and optical isomerism. We will explore these in details in the next chapter, hydrocarbon. So while we upload that video, to get instant notification, subscribe to our channel. Organic molecules, often referred to as substrate, interact with reagent in a specific way to create a new bonds. The sequence of steps that describe how reactants are transformed into a product is called reaction mechanism. Understanding this mechanism helps us predict reactivity and plan strategies. When a covalent bond breaks, it can do so in two main ways. The first is heterolytic cleavage, where the shared pair of electrons goes entirely to one atom. For example, in bromomethane, the bond breaks to form a positively charged carbocation and a negatively charged bromide ion. Carbocation like CH3+ are electron deficient species. Depending on the number of alkyl groups attached to the carbon, they are classified as primary, secondary or tertiary. Interestingly, tertiary carbocations are the most stable due to inductive and hyperconjugation effect, while methyl carbocations are the least stable. In contrast, homolytic cleavage split the bond so that each atom retains one electron, forming free radicals. These unpaired electrons make free radicals highly reactive. For instance, methyl radicals can be classified as primary, secondary or tertiary based on their structure. In organic reaction, the molecule contributing carbon to the new bond is called the substrate, while the other is the reagent. For instance, while ethane reacts with bromine, ethane is substrate and bromine is the reagent, leading to a product named dibromomethane. Reagent can either donate or accept electrons depending on their nature. Nucleophiles are electron-rich species that attack positively charged centers, such as carbocations or partially positive carbons. Common nucleophiles include hydroxide ion and ammonia. On the other hand, electrophiles are electron-deficient species like carbocations or polar molecules with partial positive charges. For instance, carbon in a carbonyl group acts as an electrophilic center. The resonance effect explains how electron density shifts within molecules with conjugated systems. For example, in aniline, the lone pair of electron on nitrogen delocalizes into benzene ring, stabilizing the molecule. Conversely, in nitrobenzene, the nitro group pulls electron density away, creating a negative resonance effect. The electromeric effect is a temporary effect observed in molecules with double or triple bonds. When a reagent approaches, the pi electron shifts completely to one atom. This effect vanishes as soon as the reagent is vanished. Hyperconjugation is a stabilizing interaction involving the delocalization of sigma electrons from CH bonds. The interaction increases with the number of alkyl groups attached to a positively charged carbon. For example, tertiary carbocations are more stable due to stronger hyperconjugation effect. Curved arrow is a key tool that we use to visualize electron movement. The starting point of the arrow indicates where the electron pair originates and the arrowhead shows where it moves. For instance, curved arrow depicts electron shifting from a pi bond to an adjacent bond or an atom, and even from an atom to a bond. For single electrons, a half-weighted called a fish hook is used to represent their movement. This helps us understand the reaction steps more clearly. In organic molecules, electron displacement can happen in two ways: permanent displacement such as inductive or resonance effect, temporary displacement which occur when a reagent attack. Take chloromethane as an example. The bond between carbon and chlorine is a polar because chlorine, being most electronegative, pulls the shared electron towards itself, creating partial charges. This causes an electron shift along the molecule known as inductive effect. Some molecules like benzene can't be represented accurately by a single structure. Benzene is often drawn with alternating single and double bond, but experimentally all its bond lengths are identical at 139 picometer. This indicates that benzene is a resonance hybrid of its canonical form. Nitromethane is another example. The difference in energy between the hybrid and the most stable resonance structure is called the resonance stabilization energy. When writing resonance structure, ensure the nuclei position remain fixed in unpaired electrons and conserved. The most stable structure follows key rules like complete octet and minimized charge separation. Organic reaction forms the foundation of organic chemistry. This reaction can be categorized into substitution, addition, elimination, and rearrangement reaction. Each type has its own mechanism and application, but once this reaction produces a compound, how do we ensure it's pure, ready for further use? That's where purification techniques comes into play. Let's explore this method starting with sublimation. Sublimation is a method where solid substance directly convert to vapor without passing through the liquid state. This technique is useful for separating sublimable compounds like naphthalene from non-sublimable impurities. Crystallization is widely used to purify solid organic compounds. It relies on the different solubility of the compound and impurities in suitable solvent. For instance, by dissolving an impure compound at a higher temperature and allowing it to cool, we get a pure crystal that can be filtered out. Sometimes a mixture of solvent is used to enhance crystallization. Distillation separates volatile liquid from non-volatile impurities or separate liquid with different boiling points. For example, chloroform and aniline can be separated because their boiling points differ significantly. The liquid with lower boiling point vaporizes first, condenses, and it is collected. For liquid with closer boiling points, fractional distillation is used. A fractionating column allows repeated condensation and vaporization, enriching the more volatile compound as vapor. This process is critical in industries such as refining crude oil. Liquids that decompose at their boiling points can be purified using distillation under reduced pressure. By lowering the pressure, the boiling points drop, preventing decomposition. This method is used for substances like glycerol. Steam distillation is ideal for separating steam volatile and water immiscible substance. The compound boil at a low temperature when mixed with steam, simplifying separation. For instance, aniline can be efficiently separated from its mixed with water. When an organic compound is in an aqueous solution, differential extraction separates it using an organic solvent, where it's more stable. The layers are separated using a separatory funnel. Continuous extraction may be necessary for compounds with low solubility in the solvent. Chromatography separates, purifies, and tests the purity of compounds. Or this versatile technique uses stationary phase, solid or liquid, and a mobile phase, liquid or gas. Based on the interaction between these phases, we classify chromatography into adsorption and partition types. In column chromatography, the mixture is separated over an adsorbent column. Compounds interact differently with the absorbent, separating as the element moves down. Highly adsorbed substances stay near the top, while the others travel further. Thin layer chromatography uses a thin absorbent layer on a glass plate to separate mixture. The solvent carries components up to the plate, separating them based on adsorption. The relative movement is quantified using the retardation factor. Partition chromatography separates substances based on their partitioning between the mobile and stationary phase. In paper chromatography, water trapped in the paper acts as the stationary phase, while the solvent moves upward, separating the components. Have you ever wondered how we detect the element present in organic compounds? From carbon and hydrogen to nitrogen, sulfur, halogen and even phosphorus, chemists have developed fascinating tests to identify these elements. Let's start with carbon and hydrogen. To detect these, we heat the organic compounds with copper to oxide. Here's what happened. Carbon is oxidized to carbon dioxide, which turns lime water milky. Hydrogen is oxidized to water, turning anhydrous copper sulfate blue. To detect other elements like nitrogen, sulfur, halogen or phosphorus, we use Lasani's test. This involves fusing the organic compounds with sodium metals. Here's what happened. Sodium reacts with the compound to form ionic compound like sodium cyanide, sodium sulfide or sodium halide. These are extracted using water to form sodium fusion extract. This extract becomes the basis for testing other elements. Let's look at each test now. To test it for nitrogen, we boil the sodium fusion extract with iron 2 sulfate, then acidifying it with concentrated sulfuric acid. A Prussian blue color confirms nitrogen. Sodium cyanide reacts with iron 2 sulfate to form sodium hexacyanidopheride. On heating with sulfuric acid, some Fe2 plus ions are oxidized to Fe3 plus, which react with sodium hexacyanidopherate to form Prussian blue. Quantitative analysis plays a crucial role in organic chemistry. It helps chemists determine the mass present of elements in a compound, which is essential for calculating empirical and molecular formulas. Let's explore the key methods used for analyzing different elements in organic compounds. To estimate carbon and hydrogen, a known mass of the compound is bound with excess oxygen and carbon to oxide. Carbon is converted into carbon dioxide and hydrogen becomes water. These are absorbed by calcium chloride and potassium hydroxide respectively. From their mass increase, the percentage of carbon and hydrogen are calculated using following formula. Percentage of carbon is equal to 12 by 44 into m2 by m into 100. Percentage of H2 is equal to 2 by 18 into m1 by m into 100. There are two methods for nitrogen estimation. Dumas method. The compound is heated with copper oxide to produce nitrogen gas collected over potassium hydroxide. Percentage of nitrogen is equal to 28 by 22,400 into V by M into 100. Geldas method. The compound is digested with sulfuric acid to form ammonium sulfate, which is reacted with sodium hydroxide to release ammonia. The ammonia is absorbed by a standard sulfuric acid solution and this amount is determined via titration. Percentage of nitrogen is equal to 1.4 into M into V minus V2 divided by 2 into 100. The whole divided by m. For halogens, the compound is heated into curious tube with fuming nitric acid and silver nitrate. The halogen forms a silver halide which is weighted. The percentage is calculated as percentage of halogen is equal to atomic mass of halogen into m1 divided by molecular mass of Ag into m into 100. Sulfur is oxidized to sulfuric acid, precipitated as barium sulfate and weighted. The formula used is percentage of sulfur is equal to 32 divided by 233 into m1 divided by m into 100. The compound is heated with sodium peroxide to oxidize phosphorus to phosphate. This solution is boiled with nitric acid and treated with ammonium molybdate. A yellow precipitate of ammonium phosphomolybdate confirms phosphorus. It's a simple yet effective test. Phosphorus is oxidized and precipitated as ammonium phosphomolybdate or magnesium pyrophosphate. For ammonium phosphomolybdate, percentage of phosphorus is equal to 31 divided by 1871 into m1 divided by m into 100. For magnesium pyrophosphate, percentage of phosphorus is equal to 62 divided by 222 into m1 divided by m into 100. To estimate oxygen, the compound is decomposed and the oxygen is converted into carbon monoxide. This reacts with oxygen pentoxide to form carbon dioxide and iodine. The oxygen percentage is derived as percentage of oxygen is equal to 32 divided by 88 into m1 divided by m into 100. And that's wrap up the chapter Organic Chemistry, some basic principles and techniques from CBSE Class 11. I hope this video gave you the clarity and confidence you need to ace this topic. Remember, understanding organic chemistry is all about connecting the dots and practicing the concepts step by step. So don't hesitate to revisit this video whenever you need a quick revision. If you found this video helpful, make sure to like, share and subscribe to our for more such concise yet comprehensive comprehensive explanation. Also, let me know in comments the chapter or topic you would like me to cover next. Stay curious, keep learning, and remember, knowledge is the key to unlocking your future. All the best for your exams, and I will see you in the next video.